chapter 7, basically about chemical reactions, right? All right, evidence for chemical reactions. We're going to have a color change, formation of a solid, formation of a gas, emission of light, emission of heat, or we could have absorption of heat. It would feel cold. Okay, all these could be signs of a chemical reaction. Let's just quick take a look here at some real life examples. So color change. So silver tarnishes, it oxidizes when it's in the presence of oxygen. That would be an example of color change. Rust would also be an example of a color change. Again, your steel is reacting with oxygen, forming Fe2O3, right? Again, that'd be a color change. Formation of a solid. If you mix, sometimes you might mix two solutions together, and if a solid forms, you'll have a chemical change. Formation of a gas. This one you need to be careful with, okay? Formation of a gas can be the chemical change, but it could also be what happens when you have a can of soda and you open it up, right? CO2 fizzes out, there's bubbles, right? But that's not a chemical change. If you have hot water burning in a kettle, or burning on a burner in a kettle and it's boiling, that's going to be gas bubbles, but it's not a chemical change. So you need to be careful with that one. Emission of light, that's a pretty much dead giveaway. You burn a fire, burn a butane lighter, what's happening? It's giving off light. You have a chemical reaction. Same thing if it's hot or if it's giving off heat. That's signs of a chemical reaction. Or absorption of heat if you have an ice pack is an example of a chemical reaction. Let me just write down, well, I guess I covered that. Let's just quick go over a couple more here. Would butane evaporating out of a butane lighter, would that be a chemical reaction? The answer is no. The butane's evaporating, right? It's going from a solid to a gas. The butane itself did not change, so that's not a chemical reaction. What about wood burning? I think I kind of used that as an example already. That would obviously be a chemical change. Your wood is going from a carbon-hydrogen compound with oxygen and some other things, turning, basically, when it burns, it actually turns into a gas, actually. What's happening, the smoke and charcoal. So that would definitely be a chemical reaction. What about dry ice subliming? You have solid CO2, you have it here in the room, what happens? It goes from a solid to a gas, right? Again, that would not be a chemical change. It would be a physical change. It's just CO2 is not breaking or making any bonds. It's still CO2. It's just going from a solid to a gas. Okay? I hope I made that clear, or somewhat anyway. Let me erase this, and we're going to talk about our chemical equation. A chemical equation has to be balanced, meaning it has to have the same number of atoms on both sides, same number and type of atoms on both sides, the reactant side and the product side. equations must be balanced. They must have the same number. I guess I'll put it over here. The same number and type of atoms on both sides of the equation. Right, it's actually pretty straightforward. Let's take a look at some examples. If I have hydrochloric acid plus sodium hydroxide, we're going to end up with, this is actually a acid-base reaction anyway, we're going to end up with formation of water and NaCl. So now, the only reason I'm showing you this is the number of types of atoms on both sides have to be the same. So we have one hydrogen here plus another hydrogen here. That's two hydrogens, that has to be two hydrogens on that side. Well, there is, right there, right? There's one chlorine here, there's got to be one chlorine on that side. There is. There's one sodium, there could be one sodium on that side. One oxygen on that side. So it's pretty straightforward. The chemical equations have to be balanced. One more example. Let's see here. Right? Now quick compare both sides to make sure that they have the same number of hydrogens and all that. Well, we'll count through, right? Two hydrogens here, plus two hydrogens here. There's two H's, there's two hydrogens. Has to be four hydrogens. Four hydrogens on that side. We have one sulfur, has to be one sulfur on that side. Have 4, 5, 6 oxygens. We got to have 6 oxygens on this side. Here we have 2. Plus 4 more, that's 6 oxygens. Did I miss anything? I counted them in G. So again, it's just got to be balanced, same number of type of atoms on both sides. That's pretty straightforward. Now we're going to have balancing chemical reactions. Balancing chemical reactions. So you're going to be given a chemical reaction, and then you have to balance the number of atoms on both sides, which you have to do. Now this is trial and error. There's no secrets. Basically, the only rule is do free elements last. Balance free elements last, okay? So balancing chemical reactions, right? Only real rule is balance free elements last. And basically, trial and error. Right? Well, let's take a look at an example. Let's see here. This is actually a combustion reaction. Not that you need to know that right now, but we have butane, butane, that's methane, methane, CH4 plus oxygen is going to go to CO2 and H2O. Now we want to balance this chemical equation, right? How are you going to do that? I'm going to write out the number of types of atoms on both sides. So I'm going to go over here, I'm going to put down 1 carbon, 4 hydrogens, and 2 oxygens. Now, oxygen is the free element, so we're going to balance that last no matter what. Now what do we have on the other side? We have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Oh, that's terrible. Now I said carbons are the same, oxygens are different, hydrogens are different. Oxygen is a free element, balance that last, all right? So what do we have? We have 4 hydrogens on the reactant side, 2 hydrogens on the product side. What do we need to do? We need to add another hydrogen over here. So we're going to rewrite it, or I'll rewrite it. Now let's count up once again. 1 carbon, 4 hydrogens, 2 oxygens. What do I have here? 1 carbon, 4 hydrogens, and I have 2 plus 2 more, right? There's 2 oxygens there. And then there's, each H2O has 1 oxygen, there's 2 of those, so that's 4 oxygens. So everything's balanced, carbons, hydrogens, except for oxygens, right? What do? I need 1 more O2 molecule, 2 oxygens on this side. They only come as O2, right? So what I'm going to do, I'm going to add another O2. And so I have 2 O2 like that. And now it's balanced. 1 carbon, 1 carbon. 4 hydrogens, 2 times 2 is 4 hydrogens. 2 times 2, 4 oxygens. 2 oxygens plus 2 oxygens, 4 oxygens. It's balanced. Okay, again, trial and error, balanced free elements last. Let's look at another example. Let's see here. Some are a little bit easier than others, obviously. Let's take a look at this one. So here's our equation. We have silicon dioxide, SiO2, plus carbon oxygen goes to silicon monocarbide plus carbon monoxide, okay? So we're just to do like we just did before. So I'm going to count up. 1 Si, 1 silicon, 2 oxygens, 1 carbon. I'm going to balance carbon last because it's a free element. 1 silicon, 1 carbon, no, 2 carbons, sorry. 1 carbon there, 1 carbon there, 2 carbons. I wrote it down here, and I'll put oxygens here. And there's only 1 oxygen. Okay? So what am I going to do? Again, balance free elements last. Carbon is free, so don't worry about carbon right now. So what am I going to do? I need another oxygen over here. So I'm going to add another carbon monoxide. It's the only way to get another oxygen, is I have to add another carbon monoxide, right? So I'm going to have this. All right, count it up once again. One silicon, oxygens, I have 2 oxygens, and then I have 3 carbons, right? 1 silicon, 1, there's 2 of these, so 3 carbons, 2 oxygens. What do I have on this side? 1 silicon, 2 oxygens, 1 carbon. So what do we need? 2 carbons, right? I need 2 carbons. I'm going to put them here. So I add plus 2 carbons, and I have plus 3 there. Okay? Let me do one more. The last one will be a little bit more challenging. Again, I hope you see this. Again, trial and error, balanced free elements last. Let's take a look at this one. You're going to take a look at butane. Burned in the presence of oxygen is going to go to CO2 plus H2O gas. Okay, so again, this is a combustion reaction, not that it really matters. Our objective is to balance this, okay? Again, balance free elements last. O2 will be balanced last. So again, count up like you do, like we have been doing. 4 carbons, 10 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Again, don't worry about oxygens, right? Balance that last free element. So what do we need though? Well, here we have 4 carbons. We need 4 carbons on this side, so we're gonna have to add 3 to here. We get 4 CO2 then. Also, what do we have? We have 10 hydrogens here. We only have 2 here. So what do you have to do? We have to add 8 hydrogens. To give 8 more hydrogens, what do you have to do? You have to add 4 H2O molecules. So it's gonna look like this. So again, I'm going to add 3. I need 3 carbons, so I'm going to add 3 CO2 molecules. So I have 4 CO2 molecules, plus, and then here, right, I need 8 more hydrogens, so I'm going to add 4 H2Os, so I'm going to have 5 H2Os. Let's count up again. 4 carbons, 10 hydrogens, 2 oxygens, 4 carbons, 10 hydrogens, and let's see here. 4 times 2 is 8, plus 5 there, that's 9 oxygens. Okay, so everything's balanced except for the oxygen. 9 oxygens on that side, 2 oxygens on this side, right? So how many more oxygens do we need? We need 7 more oxygens, right? Correct? 2 there, 9 there. You said yes, I can hear you. So yes, so we need 7 more oxygens. Well, oxygens only come in multiples of 2, correct? Here, right? So you're gonna take, we need 7. I'm gonna run out of room here. We need 7, they only come in multiples of 2, so that means we need 3.5 O2